Okay, let's go through the problems on section 5.2. Okay, number 1, it says g of x is the sum of the area under the curve, or over the curve in this part, the area between the curve and the x-axis from 0 to however far we go over. And so, since this is the integral, it's basically saying what's the antiderivative of f of t. So there's a relationship between g of x and f of x or t is it's the derivative of g. And so there's g of x, and then the derivative of it is similar to that function, and then there's the second derivative of this original function, which would be similar to the, since we got to take the derivative once here, we take the derivative once here, f prime. So there's kind of the relationship between f and g. So now, what's g of 0? Well, if we put in 0 for the x, we're taking the integral from 0 to 0. And the integral from 0 to 0 of anything is 0, because there's no width, so there's going to be no value. Then it says, what's g prime? Well, g prime, the derivative of this, the derivative of, with respect to x, of an integral from 0 to x, f of t dt, we learned in class, is just whatever this antiderivative is, capital F of t, evaluated from 0 to x, so we plug in x and we get f of x minus f of 0. And if you take the derivative of this, the derivative of capital F is back to little f with x put in it. And the derivative of a constant is 0. And so it's just f of x, or f of whatever you put in there. And we're going to put in 1 according to this problem. And 1, g prime of 1 according to this graph, g prime of 1 is f of 1, which means we go to 1 and read the graph, and it looks like it's about minus, this is 1 up, so this is minus 1.6 maybe. All it is how high is it at 1. And then the interval where g is concave, g, this one, is concaved up. If it's concaved up, the second derivative has to be positive, greater than 0. Well, the second derivative is the derivative of this one. And the derivative of a graph is talking about the slope of this. So the slope of this graph, if it's positive, the slope of that graph, the slope is positive, means the second derivative of that graph is positive. And if the slope is positive, then we're concaved up in that graph. So from here to here we have a positive slope. From here to here we have a negative slope, and from here to here we have a negative slope. So from about 1 to about 6, it looks like this has a positive slope. The function has a positive slope, which means its derivative is greater than 0, which means the second derivative of this function is greater than 0, which means that one is concaved up. And finally, the value of x where g takes its maximum value from 0 to 8. So g is the sum of the area, but we don't know where it starts. But we do know, as it's from where, excuse me, from wherever it starts, we start adding the area. Well, this area is negative, so G, not this G prime, but G is going to, the one that's adding the area, is going to be adding negative values, so it's going to go down. And negative slope means it's concave down. It's going steeper and steeper down until it gets to there, the steepest down, and then it starts, got a positive slope, so it starts concaving up, but it's still negative area we're adding, so it's concaved up till there, and then it turns around, and now it's still positive slope, so it's still concaved up, and it's gaining area. It's coming up to there, then it's concave down, but it's still gaining area. And so since this area is less than this area, the negative is only going to take part of this away. And so when are we going to be the highest? Well, it would be at the end when we add the most positive area, which cancels all that. So that means it's higher than the beginning, and it's going to be higher up here at the very end, so it's going to happen at 8 when it's the highest. Number 2. So if we integrate this, let's say this is little f of t. So if you find the antiderivative, it would be capital F of t. And we can either switch these, which would make it minus, or we can just go on with what we got here. This we would plug in, we would evaluate that from x to a, which would be f, capital F, the antiderivative at a, minus the antiderivative at x, and that would be this part. And then we have to take the derivative of this because it says so right there. So the derivative with respect to x of f of a minus f of x would be, the derivative of a constant is 0, and it would be minus, and the derivative of f, well, this is f, this was the derivative of it, because we called that the antiderivative. So this is the derivative, which would be ln of, and now we're putting x in place of the t, so we put x here. And then we take the derivative of the inside, where the derivative of x is just 1, so times 1, so that's the answer. Turns out if you got the derivative of the outside of the integral from a constant to x, you just put x in place of the t, and since this is going the wrong way, and not a to x, but x to a, we have to take the negative of it. So there's the answer. Now this one, f prime is this, and if you graph that, it looks something like that. And I should probably do that. So where's my calculator? Let's graph that. And you can do it on Desmos or on a calculator. So I got to graph e to the negative x squared divided by 5. Zoom, let's see, we got to go, yeah, let's just go zoom 4. And so I got this screen. If you got an older calculator, it won't go up far enough, and you'll have to widen it out to see it up to 4. But 0, 1, 2, 3, 4. We can see all the way up to 4. Now, if that's the derivative, then f is the area, the change in f. The change in f is equal to the area under f prime. Well, if that's f prime, and we want to find how much it changes. We can find out how much it changes from 0 to 4 by doing, second, calculate the area under this curve from 0, enter, 4, enter, and it says the area is 1.959. So this area is 1.959. That's the change in f. The area under the derivative is the change in f. Okay? But f started, this is not a picture of f, this is a picture of f prime. So f started at 1, 2, 3. And by 4, from 0 to 4, it changed by 1.959. It increased 1.959. So if it starts at 3 and it increases by 1.959, the height is 4.959. Number 4. So f of x is adding the area from 2 on under this curve. So if we go backwards, we'd be subtracting off because the limit would be backwards. Okay. And it says this area is 4.29. This area is 12.75. This area is 0.36, and this area is 1.79. And assume further that the portion of A2 that lies between 0.5 and 2, the area on this side is 6.06. Excuse me. Okay, so if we're going to graph the area, and we know that at 2 it's 0, then sorry. Okay. It goes up some. If it's 606 on this side, it must be 6.769 on this side, because that plus that would make the 12.75. So between 2 and 4, it goes, and it's supposed to be 0 at 2. It has to go up 6.69. 5, 6, 7, 8, 9, 10. So that's about the spacing. 6.69 would be about there, and that's by 4. Now what's its shape between there? Negative slope means it's concave down, and it's negative slope from 2 all the way beyond this. It has a slope of 0 at 4. So it's concave down, and it's increasing pretty much. It's like a slope of 6, steep, and then it goes to 0 slope, concave down, and then it continues getting steeper down clear till 4.5, and then it starts getting positive slope. By 5 it has a 0 slope, and it has to go up. How much did it come down? Well, we were at 6.69, and then we lose 3.6, which should take us back down from 6.69 high down to 0.36. From this would be 6.23. Well, that's too much down. 6.23 would be about here. So it just curves down slightly, comes down just a little bit. And then we add 1 point, and that's by 5. And then we add area, the positive slope, so it's concaved up and then concave down. Concaved up because the positive slope, concave down. And we have to gain 1.79. So 79 plus 23 is 82, 92, 102. So it's going to be 67802. 8, 5, 5, 6.5, no, 7.5, 802. So about that high at this point. And so it's curved up till we get to about 6, and then it starts curving down. Okay, to go backwards, this was 606. We're at 2, so we have to go down by a half, down 606, so negative 5, negative 606, somewhere down here at 0.5. It's still positive slope, so it's concaved up till it gets to there. And then before that, and it's going up because this is positive area. This says it's going down, so we have to be coming down. And from here to there, it has to come down 4.29. We're at, if we take 606 off of 0, we're at negative 6.06. If we add 4.29 to that, we get 1 point something. 1 point something. We're at about here, and it's that's negative slope, so it's concave down till here, and then it becomes concaved up because the slope changes to positive. So we have concave down, concaved up, and to get this number exactly, we got to go minus 6.06 plus 4.229 because it's coming down that much, so going backwards we have to add that. So we're that's negative, that's positive, so we're actually subtracting. 9 from 16 is 7, 2 from 9 is 8, because we had to borrow from here, so it's 5, 9, and then 8, 5, 9. 5, 9, to borrow the 1. 2 from 9 is 7, and 5 minus 1 is 1.77. So we're at minus 1.77. Okay? And I talked about the increasing, decreasing, concave up, concave down, and where is it? 0. 0. I talked about all the curvatures. Okay. Number 5. Number 5 says tide is removing sand at some sort of rate, and this happens in the beaches. I did a lot of beach hiking, and there's times when the tide just completely removes all the sand from a beach if you're on the ocean beach, and then another tide or different action will bring it back. This happens to be a beach where people are trying to put sand back on the beach. So the net change in the sand would be the sand that's being put back minus the sand that's being removed by the tide will be how the total sand is rate of change. So it's kind of the derivative of the total sand. because this is the rate of adding, this is the rate of removal, and so this becomes the rate of change of the total sand. So, write a definite integral that measures how much sand the tide will remove between 0 and 6. So it's the integral from 0 to 6 of the sand being added minus the sand being removed, evaluate over that time, 0 to 6. Write an expression for y of x for the total number of cubic yards of sand on the beach at time x. So y of x would be equal to wherever they want to start it at, where it's 0. I don't know where you want to start it. So we'll just say a to x of the net change. So we'll have to do s of t minus r of t dt. And this would be a function of x. So we're going to measure from some time to some time the change in it. This should be added to the initial starting amount. So whatever you start at, let's say it's 0, then this would be. So we have to know how much y of 0 is. And so they would have to tell us y of 0 equals so much, so we know that the exact number of cubic yards of sand at the beach at that time. Okay, hopefully I explained that carefully. At what instantaneous rate is the total number of cubic yards on the sand at time 4 changing? So this is the rate of change, just this inside part. So we would do S of 4. What's the rate of sand being added minus the rate of the sand is being removed. And so this will be the rate of change of the cubic yards of sand. So we would put 4 into the function. So we have to go back up to here and put 4 in. So we get, let's see if we can see it there. Okay, we're going to get 15 times 4 over 1 plus 3 times 4. That'll be how many cubic yards of sand per minute added to the beach per hour, minus how fast the tide is taking out, which would be 2 plus 5 sine of 4 pi, putting in 4 for the t, over 25. And that'll be how fast the sand is changing. So I'm going to type in this function. I'm going to type it in a little differently than we did in class, just so that you can see another technique here. So I'm going to type in s of t, set alpha y equals, press enter, and I get a fraction. I put in 15x, and in the denominator 1 plus 3x. In the second one, I'm going to put 2 plus 5 sine parenthesis alpha second, make it a fraction of 4 alpha pi x divided by 25, close parenthesis. Oop, not there. Delete. And I actually put an extra parenthesis in here. Sine already comes with that, so take that out. And one at the end. And there's y2. And I could graph those, but I don't want to. So I'm going back here and press enter, and go up there and press enter. What I want to graph is the sign being added, which is y1 vars y variables, function y1 minus vars, which is right here, vars, y variables, function y2, and that's what I want to graph. So I'm going to go make sure my mode is in radians, and I'm going to go zoom 6, see if that gets enough. Okay, when I do zoom 6, I see that it says the amount of sand being added minus the amount of sand removed turns out to be negative, so that means on the net it's losing sand, and it stays negative even though it goes up and down. It's staying negative all the way up till sometime here, 1, 2, 3, 4, 5 hours and something later. It's all that time it's losing sand. Then after that it starts gaining sand. So when they say over the time interval 0 to 6, at what time is the amount of sand on the beach the least? So if it starts out at some level, we don't know what level, but it's losing sand all the way up to here, then it's going down, 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 down faster sometimes than other times, but it's going down all the way up to here, and then it starts adding. Then that will be when it's the lowest, and that time is, second, calculate the 0. It looks like it's somewhere between 4 and 6. 4, enter 6, enter, I'm guessing 5. It says no, it's 5.11. 7, so 5.12 hours. Into this is when there'll be the least amount of sand on the beach. Okay. And finally, this one. So when it's at a height of 0, it's climbing at 925 feet per minute. When it's at 1,000 feet, it's climbing fewer feet per minute, and so on. And they ask us to write this function, how many minutes to climb depending on the height. And so if you're at a height of 0, how many minutes does it take to climb 925 feet? Well, it'll do 925 feet per minute, which means it's going to do a very small fraction of a minute to do that. It's going to be 101 over 925, 101 over 925th of a minute to climb 1 foot. And this would be 1 over 875 minutes to climb a foot. 1 over 830 minutes to climb a foot. 1 over 780 minutes. 1 over 730, etc. So we did that. That's A. Give a careful interpretation of the function whose derivative is this. So I'm going to think about this being the derivative of some function. So I'll call that function m of h, capital M, the antiderivative of this. So if I were to graph this, just so we understand what's going on here, as the height increases, 0, 1,000, 2,000, 3,000, and I graph these on 1 divided by 925 is a small number, 0.001. So I'll put here 0.001, and it's about 0.00108. So right, we start round there. Then what's 1 divided by 875? You notice it's slightly bigger. Not much, but slightly bigger. And if I go to the next one, 1 divided by 830, notice it got bigger, 1.0012. So it's working its way up. These keep getting smaller, and a fraction with a smaller denominator gets bigger. And I'm not sure the shape of the curve other than it's increasing. I don't know the curvature. I could try to figure that out, but I'm not interested in that. So if I write a function that's the capital M, it's looking at how much area is under the curve. And the area would be this, which is in minutes per foot, times this way, it's in feet or foots. So if I take feet times minute per feet, I end up with minutes. So the area under the curve is the total minutes. And that's what an antiderivative gives you. The area gives you the change in the total minutes. So if they take off at 0, the area under here would be how many minutes it takes to get to 1,000, then to 2,000, then to 3,000, and so on. If we start some minutes later, then here would be how much time changes to the time when we get to 1,000, and to 2,000, and to 3,000. So we don't know what C is, what time they're starting this ascent, but the area represents the change in time to get at these different heights. So that's a careful interpretation of this. The input is heights, and the output is going to be the area, which is going to be the number of minutes to get to that height. That's what capital M of H, the antiderivative, or the function whose derivative is this, which means it's the antiderivative. Determine the definite integral whose value gives you exactly the number of minutes to get to 1,000 feet. Well, it would be the antiderivative, or the area under M of H, with little tiny h's, evaluated from 0 to 10,000 feet. Clearly explain why the value of this integral has the required meaning. If we start at 0 and the plane takes off at 0, this up to 10,000 gives you the change in time. And so if you start the time at 0, it's going to be the amount of time, the number of minutes to get to 1,000 feet. The formula for M of H. So now we want a function that we can put in on H and get how much minutes have accumulated. So instead of just putting 1,000 here, we want this to change. So we can go M, well, I'm going to do capital M. I'm just going to put an X here, where the integral goes from 0 to X of little m of H dH. So now we're going to add up the area as we go from 0 to any point. Add up the area from 0 to any point of the area under this curve, and that will tell us how many total minutes to get to that x heights. So here's a m as a function of what height you want to do by finding the area under this curve to that height. And now estimate values for m of 6,000 and to 10,000. I'll do the trapezoid. That's probably the most complicated one. You can do midpoint, you can do left or right. I will do trapezoid, which means we're going to do intervals from, I'll just do intervals of 1,000. So the width of my bars doing bars under here, I'm going to find the width of the bars 1,000, and I'm going to take the average of the two heights, which are these two numbers. So I'm going to do 1 over 925 plus 1 over 875 divided by 2 plus the next interval will be 1 over 875 plus 1 over 830 divided by 2 plus 1 over 830 plus 1 over 780 divided by 2 plus 1 over 780 plus 1 over 730 divided by 2. Boy, this is messy, but this is what we'd have to do the trapezoid. 1 over 730 plus 1 over 685 divided by 2 plus, and so on, all the way up to the last 490 plus 440 divided by 2, 1 over those. So, however, I get half of this plus all of that, half of it here and half of it there, half of that one and half of that one, so I get all of that one, all of them, all of them, all of them, and only half of the last one. So it would be 1,000 times, and I got to do it up to 6,000. 6,000 was the 635, so that'd be 1 over 685 plus 1 over 635 over 2. So I'd be done there if I'm only going to 6,000. So I get 1 over this divided by 2 plus this one 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 plus half of that one. So on. We are going to do 1,000 parenthesis 1 divided by 925 that thing divided by 2 plus 1 divided by 875 plus 1 divided by 830 plus 1 divided by 780 plus 1 divided by 730 plus I got to do 685. 1 divided by 685, and then the last one I only do half of that one, plus parenthesis 1 divided by 635 close parenthesis divided by 2 close parenthesis. Half of the first one, half of the last one, and all of the ones in between. And I get 7.787. $7.787, and this would be calculating the number of minutes to get to 6,000 feet. Now to go to 10,000 feet, I can bring back what we had here. I just need to keep going here, so I'll do the, delete that parenthesis, do the 165 plus 1 divided by 585 plus 1 divided by 535 plus 1 divided by 490 plus, now I'm going to do half of the last one here, so that's 1 divided by 440 divided by 2, close parenthesis, enter, and I get 18.74. Now, I had some people do midpoint, and that would be the easiest. It would be fairly accurate doing midpoint because this is a fairly straight line up here, so it's not changing by a lot. So let's do the midpoint one here. So if we're going to go to 6,000 feet for the first answer, we'd go from here to here. There would be the midpoint. Here to here, that would be the midpoint. And here to here, that would be the midpoint. So we'd want to do parenthesis simply 1 divided by 875 plus the midpoint of the next one, 2,000 to 4,000 would be at 3,000. 1 divided by 780 plus, and then 4,000 to 6,000, midpoint at 5,000, be 1 divided by 685, close parenthesis, times the width of the interval. So I'm doing 2,000, 2,000, 2,000. My widths are 2,000. And that gives me 7.769. It gives me a little bit lower estimate than the trapezoidal, but not a whole lot different. This is 7.77 rounded. This is 7.79 rounded. So it gives me 2/100ths difference. Okay, 2/100ths difference here. And I could do that here, midpoint, I would just have to do 1 over that and 1 over that. So 1 over that, 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 midpoint rule times widths of 2,000. Okay.